I started talking about symmetric functions last time, and as I said earlier, this will be a crash course. I won't give many. I'll hardly give any proofs. But these are things you can read up. I mean, it's not advanced material. It's just a lot of it. So I won't have time to explain everything. So I started by defining what a symmetric function is formally. It's a formal power series in infinitely many variables, and that's why these are polynomials essentially, but because they have infinitely many variables, we use the term symmetric function instead of symmetric polynomial. But many times we will focus on finitely many variables, and then it's of course a symmetric polynomial. So I defined what a symmetric function is. I mean, it's the natural definition, and as I said, we are free in general to choose coefficients from a ring, from a commutative ring, but we will focus on the rational numbers just because of convenience. Then the space of symmetric functions becomes a vector space, and it's also an algebra, and it's graded. So once we know that it's a vector space, we can ask about distinguished bases. So I spent the rest of the class talking about the standard bases. So the monomial symmetric functions is the first one. You take a monomial in many variables, and then you just apply all possible permutations to get the symmetric function. So m lambda is the notation for the monomial symmetric functions. Then I talked about elementary symmetric functions, which are where every monomial, every variable has degree at most 1, and if it's of degree n, then you get en, and then e lambda you get by taking products over e lambda i's. So I should have said that the lambda n is the notation for symmetric functions of degree n, and the cardinality of that vector, the dimension of that vector space is the set of partitions, the number of partitions of n. So they are naturally indexed by partitions. So the monomial symmetric functions are, of course, defined, naturally indexed by partitions, and the elementary symmetric functions, you take products over the parts of the partition. So I described those, and then I talked about the complete symmetric functions, and then the power sum symmetric functions, and I added two structures to this space. One is the natural scalar product, although what is natural here may not be obvious. In the sense that this notion of a scalar product comes from other considerations which I'm not describing. So in this scalar product, we require, the definition is that the monomials and the homogeneous symmetric functions are dual, and in that case the power sum symmetric functions are orthogonal but not orthonormal bases. And we define this endomorphism omega, which takes the elementary symmetric functions to the homogeneous symmetric functions or the complete symmetric functions, and it turns out that that's an involution, and it acts nicely on the power sums. And I ended with a question about having a natural orthonormal basis in lambda, and asking whether there's an integral orthonormal basis, namely this, if we call this basis b lambda, is there a basis b lambda which is z linear in the monomial symmetric functions? and for which the monomials are also set in these spaces. And so I ended with that, but one thing I forgot to do in the last class is to show you how the involution works in Sage. So I remind you that symmetric functions are defined this way, and there's this handy shorthand, a handy command rather, which is defines all the bases in one shot. So E is the notation for the elementary, H for the homogeneous, M for the monomial, and P for the power sum. Now you can forget about F for now. And S is this Schur basis, which I'm going to talk about presently. So I have already uploaded this on Kuka, and you can look at it. And so I wanted to just show you how to see the action of the involution. So I defined F as this monomial symmetric function with for the partition to 1, and then F dot omega gives you this. So we can check E. We can check the action of E lambda for so the command is dot omega. So for line partition 3, let's say. So the answer it's going to return in the E basis. So E111 turns out to be itself. But if we want to check that E acts naturally on H, I mean the definition of omega, that is omega of E is H, then you can see this, and you can do the converse thing also, just to check that it's an involution. So I do E of H and I get okay. All right. So now let me begin with this new symmetric function. So what number was that? So 4 was the power sum. So I'll start with the 5th one, which are called the Schur functions. And in some sense, these are the single most important class of symmetric functions, and we will also need them when we talk about generating functions of plane partition. So there are many ways of defining them, at least 4 natural ways, and I will give the combinatorial definition, which seems a bit ad hoc, but is natural in a sense that it is naturally involves infinitely many variables. So as I said before, symmetric functions are naturally defined using infinitely many variables. So let lambda be a partition of n, a semi-standard tableau. So I have defined standard tableau before, maybe in the first week or so. So this is a generalization of that. So a semi-standard Young tableau or SSYT of shape lambda is a filling of the Young diagram of lambda by positive integers that is weakly increasing along rows and strictly increasing along columns. Notice that we are not restricting the maximum size of the positive integer. So if T is an SSYT of shape lambda, we write SH of T is. Okay, so it's the underlying partition. So let's give an example. So let's say lambda is 5311. T is, so I'll not write the box, I'll not draw the boxes, I'll just write the numbers and you can see where the boxes are naturally. So 11134, 244, 5, and so on. Okay, so it's strictly increasing along each column and it's only weakly increasing along each. So to compare with the standard tableau, so this is maybe why this notation semi, is that standard tableau was a filling of lambda with 1 through n, the size of the partition, which is increasing, strictly increasing in both directions. Okay. The type of T alpha equals alpha 1, alpha 2, dot, denoted alpha equals type T, is a decomposition where alpha I, which is the same as alpha I of T, is the number of parts of T equal to. So in the above example, type of T, let's see, so how many ones are there? That's alpha 1, so that's 3. How many 2s are there? 1. How many 3s are there? 3, 1, 3, 3 4s, 1 5, no 6, 1 7, and all the, then after that you have an infinite sequence. So this alpha is clearly a weak composition of n, the size of the partition. Right? So in this case, to sum the entries, you get 10. Okay. For an SSYT T of type alpha, we write x to the t, which will mean x1 to the alpha 1 of t, x2 to the alpha 2 of t, etc. So it's a product. It's a finite product because it's a weak composition. So again, in this example, x of t was x1 cubed, x2, x3, x4 cubed, x5, etc. Okay. All right. Okay, so here is the key definition. So there's something non-trivial already in the definition. So let me. So this. Okay, the Schur function S lambda. So the standard notation for this is S lambda indexed by partition lambda. In the variables x1, x2, etc. is the formal power series. Okay, so I don't know what is that. Is given by S lambda equals sum over all t shape where shape of t is lambda x to the t. Okay, so you take all possible tableaux, all possible semi-standard tableau, and you know, for each of them you take you look at the type and you take x to the t, and you construct this formal power series. So it's an infinite series because there's no bound on the size of the maximum integer. So this is the Schur function. Okay, so let's do an example. So for now we don't have any property of this other than the fact that it's a function, it's a formal power series in infinitely many variables. Let's look at an example. So let's take lambda. So let's take a simple example, 2, 1 with maximum entry at most 3. Okay, so let's just list down all of these. There are not too many. So I'll write the tableau here and I'll write x to the t. So let's start with the simplest one. So 1, 1, 2. Okay, maybe you can tell me more. So this has weight x1 squared x2. Next. Any volunteers?
113.
113. Next.
1, 2, 3.
1, 2, 3. Yes. So that's x1, x2, x3. Go ahead.
1, 2, 2.
1, 2, 2. Nice. x1, x2 squared.
1, 3, 2, 1, 3, 3.
1, 3, 2.
1,
1, 3,
3.
3. Nice. So this is also x1, x2, x3. Notice that these two have the same weight. x1, x3 squared. Yes? I heard something else.
2, 2, 3 and 2, 3, 3.
Very nice. Yeah, I was I was trying to catch you on that. So it doesn't need to start with 1 either. Yes, very nice. So x2 squared, x3, and x2, x3 squared. And I think that's all. So that says, so if I if I force myself to stay under 3, then that means what I'm doing is I'm setting all the other guys equal to 0. So x3 and 0, 0. Right. So this I will write as, this is a general principle that we'll just write this as, so this belongs to lambda 3. Well, okay, not yet. Okay, let's just see what this is. So I have x1 squared. Okay, so maybe I'll not write it I'll not sum it all over again, but if you notice, so let's just observe the symmetry property, if any. So I have x1 squared x2, and now let me permute this over all. So this you can think of as x1 squared, x2 to the 1, x3 to the 0, right? So I have I can apply all permutations in S3 to these, depending on your taste, either the exponents or the indices. But if you apply all the permutations to those, you will see that they are all here, surprisingly. So there is x1, x2 squared, that's here. Then there is, so those two correspond to, I mean, those two have x3 exponent 0. Then if you want to look at x2 exponent 0, you have x1 squared x3, and you have x1 x3 squared. And if you want to force the x1 exponent to be 0, you have the last two, x2 squared x3 x3. So in fact, you have the monomial symmetric function in the partition 2, 1 of x1, x2, x3. So you have 6 terms over there. And you have x1, x2, x3, which is already symmetric in the 3 variables, and that's precisely the monomial symmetric function 1, 1, 1. So this is 2 times and 1, 1, 1 in x1. So rather unexpectedly, even though this definition does not imply it in any obvious way, it turns out that we ended up with a symmetric function. And so this is no accident, and that's the point of the next theorem. So this theorem I will prove. It's not hard, but so S lambda belongs to lambda, and in particular S lambda of x1 to xn belongs to lambda. Okay, so let's prove it. So since S lambda of x should be invariant under any permutation of n, interchanging finitely many positions, it suffices to prove that S lambda is invariant under the interchange of xi and xi plus 1. So if we can show this for any I, then we are done. Okay. Okay. So let alpha, let lambda be a partition of n, and alpha, which is alpha 1, alpha 2, etc., be a weak composition of n. Then set alpha tilde to be same as alpha, except interchanging alpha I and alpha x. So these two are interchanged from alpha. Okay, and so we have and define j lambda alpha to be the set of SSYT T such that shape of T is lambda, type of T is alpha. So, right. So we have all these tableaux contributing with this to the same shape and type. So all of these will have the same weight because their weight is the same, is their type is the same. So what we want to do is to find a bijection between j lambda alpha and j lambda alpha 2. Right? So bijection phi from j lambda alpha to j lambda alpha 2. If we do that, we are done, because the cardinality of this is just going to give you the coefficient of x to the t, and if these two are the same cardinality, we are done. So we'll actually, well, we don't necessarily want to find a bijection. We want to show that j lambda alpha and j lambda alpha tilde have the same cardinality, but we'll do this by finding an explicit bijection. Okay, so let's do that. So let T belong to j lambda alpha. Oh, actually, this is not a j. Okay, sorry. This is curly T. T for tableau. And focus on the parts of T equal to either I or I plus 1. Okay, so we don't care about any of the other parts. So if lambda is like so, you know, where can I and I plus 1 be? So you know, they can be they can be in a row. I mean, it's weakly increasing, so you can have any number of i's followed by any number of I plus 1s, or in a column, so there can be many more, and then there can be more somewhere there, you know, it doesn't matter. But if in a column, you can have at most 2 of such guys. This is because of the strict decrease condition. So what can happen? The only things that can happen is an I can be followed by I plus 1, or you can have just one of them, I or I plus 1, so in another column, or you can have nothing. Right? So is that clear? So in any column, there are 3 possibilities. It contains neither I nor I plus 1. It contains both I and I plus 1, like in this example, or it contains only one of I and I plus 1. Okay, So if it contains neither I nor I plus 1, I don't care. I mean, we don't do anything to that column, right? And if it contains both, so because there's the cardinality is preserved, cardinality of both I and I plus 1 is the same. So for both these guys, and in this case, again, the cardinality of both these guys is 1, so I don't need to necessarily change. So the only problem happens if there is exactly one of these guys. And it could well be possible that there's an I here and I plus 1 here. So these could be, separated all over the place. So we have to see what's going on. So we have to focus on this latter set. Oops, sorry. So focus on the latter. So what is the general structure? So what is the most general configuration that they can reside in? Is the following. So I claim this is the most general thing that can happen. So we have to see this a whole blob. I mean, what is the most general blob that contains I and I plus 1? So I claim this is the most general structure. So I have maybe draw some rectangles. Okay, no matter. So I have I, etc. So I have a bunch of I's. Then I have a bunch of I plus 1s. And what can happen both before and after? So let's say there are R of them and there are S of them here. And before this, there could continue to be I's. So I. But below them, there is I plus 1s. So these are columns of the type 2, which contain both. Okay. And similarly, over here, you could continue to have more I plus 1s. Such that above them, there are I's. Okay. Is it? So I claim that this is the most general configuration that can happen. If you have a singleton, so I mean, you can give some names to these. So this is R0 and this is S0. If you have just one of these, then that corresponds to, let's say, you have only one I, that corresponds to S0, R0 being 0. If you have only one of these, that corresponds to R0 and S0 being 0. But you cannot have anything more complicated than this. Is that clear? If there are any questions, please ask. You cannot, for instance, have anything I mean, you could potentially you could potentially have more I's here. No, you can't. So I mean, you might think that you have an I here and something else here, but that's not possible because whatever is here has to be greater than I, strictly greater. And then if it's not I plus 1, that fails the weakly increasing condition. And similarly, for the same reason, you cannot have an I plus 1 here because whatever is here is strictly less than I plus 1, and if it's not I, okay. So this is the most general. So a general blob which contains both I and I plus 1 is like that. They are of course degenerate cases, and there could be many of these separated all over the place over lambda. There could be one here, etc. In different columns, of course, not in the same column. Okay, so So whatever, okay, so I should have left some space here. So let me put R here, and whatever is here by definition is greater than R I plus 1. So, okay, so whatever you have over here cannot be equal to cannot be equal to I plus 1, because then it's subsumed here, and so this is the maximal such guy, for example. And whatever is here is strictly less than I, right? By the same argument. Okay, so this is that. Okay. All right. Now it's easy to see what to do. So now I define the phi of such a tableau. Let phi of t be the tableau with SIs with SIs and R pen is and R I plus 1s in each such block simultaneously. Okay, and then this is clearly an involution. I mean, yeah. So if you act on such a block again, they will exist. So we don't do anything as promised to this block of R naught and this block of S. Okay, and then the number of R's and S's. So the T tilde that you get over here will have the number of ones and number of i's and I plus 1s interchanged. Okay, this is clearly a bijection with the desired properties. Okay, so it's a nice elegant result. So for example, let's go back to lambda being 2 1, and let me take the tableau 1 1 2, the same example as before. T equals 1 1 2, so alpha is 2 1 0. I'm taking the maximum entry to be 3. So if I take I equals 1, so then then this tableau is exactly like this, 1 1 2, just that part. So phi of t is then 1 2. So in that case R is 1 and S is 0, so you just take the other fellow, and if I is 2, then phi of t, what will it do? So then we are comparing 2s and 3s. So then this is a singleton 2, it's like that. R is 1, R naught, S naught, and S are 0. So you just change the 2 to a 3. Right? So that's how it is. Okay. Any questions about any of this? Okay. So let me define another quantity. So let lambda be a partition of n and alpha a weak composition of n. Then k lambda alpha is the number of SSYTs. So it's the cardinality. So it's the cardinality of T and alpha, and is called the Koska number. And so S lambda is the sum over mu partition of n, because this doesn't depend on alpha. I mean, by interchanging alpha I and I plus alpha I plus 1, this doesn't change, this cardinality does not change, and so I can rearrange alpha to make it a partition. Okay, so by the previous theorem, what we have is by the above theorem, then you get mu. Right? So so it's enough to look at partitions. Okay, so right. So I should tell you that these numbers are in general hard to compute. So there is no clean formula known for these in general. For lambda equals 1 power n. So remember I showed you the frequency notation last time. So this is just the partition 1 on 1 n times. For lambda equals 1 power n, k lambda mu, mu equals 1 power n, so k lambda 1 power n is given by the Hooke length formula, which I showed you many weeks ago. Because these correspond to standard term. Okay, but otherwise there is no general formula for these. Okay, so so now I want to claim that these in fact form a basis. So to do that, I'll state a result which I won't prove, but which is not too hard to prove. But before that, I need an ordering on partitions. So does everybody know what a partial order is? Is there anybody here who does not know what a partial order is? Okay, so so recall the notion of a partially ordered set, which I will not get into. I'll post that. So it's a set together with a relation which is reflexive, anti-symmetric, and transitive. So we will. So here's the definition. So the dominance order on the set of all partitions of n is as follows. Mu is less than or equal to lambda if mu1 plus up to mu k is less than or equal to lambda 1 plus up to lambda k for all k. So here I mean, you pad them with zeros and then you compare the inequalities as regular integers. So For I think up to 5, this is a totally ordered set, and then 5 onwards, there are partitions which are not comparable. So I think this is an example. So for n equals 6, 4, 1, 1 and 3, 3 are incomparable in the dominant set. So 4 is greater than or equal to 3, but 4 plus 1 is less than or equal to 3. Okay, so you cannot say any one of these is less than. Okay, so this is an important order, and it helps simplify many proofs. So it's a good reason for defining it this way. Defining this, I mean. So suppose mu and lambda are partitions of n. If k lambda mu is non-zero, then mu is less than or equal to. Moreover, k lambda is 1. So this is so I'll not prove this, as I said. Let me illustrate this. So let's go back to Sage. So as I said before, when you use this inject shorthands command, you get the Schur basis also. So this you get the Schur functions also. So S is the shorthand for that. So S21, for example, if I write, you can expand this in 3 variables to see our example. So you get all the 8 ones that we did earlier, the 8 examples we saw earlier, with the coefficient of x1, x2, x3 for us being 2. And you can also expand S21 in the monomial basis, and you get what I wrote earlier. Okay. So again, repeating what I said, what I emphasized several times in the last class, this expansion turns out to be independent of the number of variables. So here it was 3 variables. If you had taken just 2 variables, then also you can see that you would have only 2 partitions, this one and this one. In that case, this guy would be 0 because x3 is 0. So you would have, so the appropriate reduction works. So then you would have S21 would be M21, which corresponds to x1 squared x2 and x2. Right? So that's the advantage of dealing with infinitely many variables. Okay, so let me also show you the transition matrix. So let me copy this. So let me expand S in the M basis, and maybe I'll do it in the partitions of 3 first. So you get an upper triangular matrix. So 4 is okay, 5 is also okay, but 6 onwards you start to get holes. But it is still true that it's upper triangular. So in fact, this proposition that I just stated, so notice that the diagonal entries are all 1. So these are sometimes called unitriangular, upper unitriangular matrices. So these are matrices which are upper triangular and have diagonal entries 1. So they form a group. That's one reason for studying them. But the other thing is, because of this property, if you go the other way, so okay, so if I expand M in the S spaces, you will also get integers. You will also get upper triangular matrices again because of this group property. So this shows that the Schurs, not only do the Schurs expand integrally over the monomials, the converse is also true. Okay, so a corollary of this is that S lambda, or lambda partition of n, is a basis for lambda n, and therefore if you take all possible S lambdas, you get a basis for the entire ring of symmetry. Okay. All right. So two other properties of the Schur functions, which is what makes them very nice, is the fact that okay, I can state it. So this is a theorem that S lambda S mu is delta lambda. So i.e. S lambda forms an orthonormal basis for lambda. Okay, so in some sense they are the nicest basis. So remember, the p lambdas are orthogonal but not orthonormal, and s lambdas are orthonormal, and so this answers the question that I had posed at the end of the last class. Yes, there is a natural orthonormal basis, and yes, there is the same basis is satisfies the second property, and as I showed you in this example. Okay, so it's really one of the nicest, I mean, the nicest basis in some sense. The other property which I wanted to explain is a state again without proof, is the action of omega, this involution. So if I act by S lambda on omega, I get S lambda, the conjugate. So it's the Schur function on with the index by lambda goes to the Schur function index by lambda. So I can show you both of these properties. So here we showed that the p's are orthogonal but not orthonormal, and here if we do s, if I take the scalar product of s lambda with s mu and I run over all partitions of phi, I get the identity matrix. And the other thing I can show you is this action of omega. So S lambda dot omega. So maybe I just you'll see lambda and S lambda. S lambda and S lambda dot omega. You see, you'll get the conjugate. So I can go higher just to show you that this is not an exception. So you can see things like this happen. Okay. So good. So these are some of the fundamental properties of S lambda. But another definition of the Schur functions is is going to be useful for us because these are somewhat difficult to compute the way I have explained them. So let me just a second here. So let me go back to the to another definition of the Schur functions, and this is in fact the original definition. So actually original definition of Schur functions. This is due to Cauchy. So now we will fix the number of variables. Okay, so we will fix n variables x1 up to xn. Okay. Okay. So for any weak composition alpha, which has n indices, so it belongs to n to the n. Define the skew symmetric function polynomial rather a alpha of x1 up to xn to be sum over all pi in Sn, symmetric group, sine of pi times x1, x to the alpha essentially, x1 to the alpha 1, x2 to the alpha 2, etc., xn to the alpha n. Okay. And notice that by the usual, oh sorry, what am I doing? X pi 1 to the alpha 1, x pi 2 to the x2 to the alpha pi 2, etc., xn to the alpha pi. Otherwise, this did not depend. And by the usual Leibniz expansion, this you can see immediately is determinant, the n by n determinant of xi to the alpha j. Where I j run from 1 through. So you can see immediately either from the first definition or the second consequence that if any two indices are equal, you get 0, and otherwise, if I interchange alpha I and alpha j, I'll get a minus n. Right? So therefore, without loss of generality, assume that these are distinct, alpha 1 strictly greater than alpha 2, etc. And the last one, of course, can be 0. So, in particular, let delta be the first non-trivial such guy, which is n minus 1, n minus 2, etc. up to 0. And for any partition, for any lambda partition of, lambda such that length of lambda is less than equal to n, define alpha to be lambda plus delta. Okay. Okay, so the first thing you notice, maybe I should define this later. Then, Then what is A delta? A delta is the determinant of xi to the n minus j, right? Alpha j is n minus j, j going from 1 to n. And this you have seen before, is already given in one of the homework problems, homework 1. This is the van der Waals determinant. So it's 1 less than equal to I less than 3 less than equal to n xi minus xj. Right? So we have seen that before. And now I want to look at A alpha with this more general alpha. So if lambda were the empty partition, this would be A delta, but I can do something more general. So A alpha, which is A lambda plus delta, is a kind of generalized van der Waals determinant. So it's the determinant of xi to the lambda j plus n minus j. Right? And this is also a skew symmetric function of the xi's, right? By the same explanation that I gave earlier. So in particular, this means that this is divisible by each xi minus xj. So therefore, it is divisible by A delta. Okay. So since A lambda plus delta is divisible by A delta, their ratio is a symmetric polynomial. This is anyway a polynomial, and you know, I've said that this is divisible by A delta because it's divisible by each of these factors. So this is a symmetric polynomial in x1 up to xn. Right? And the fundamental theorem in this connection, so you get some symmetric polynomial. So this belongs therefore to, so the ratio A lambda plus delta by A delta belongs to lambda, capital lambda n. So A lambda plus delta by A delta belongs to lambda n. Right? So it's a symmetric function. But this, the fundamental theorem over here is that A lambda plus delta by A delta is the Schur function S lambda. So here notice, maybe I didn't emphasize it earlier. So if I take lambda plus delta, I am guaranteed, and lambda is a partition, I am guaranteed to have distinct parts in lambda plus delta because these are weakly decreasing, and I am adding strictly decreasing numbers delta to them. Right? So these are strictly decreasing numbers. So this guy is non-zero, and so so then you get some symmetric polynomial after dividing by delta. So Cauchy called this the bialternant formula. I mean, at that time, I don't think the term determinant was popular. So such determinants were called alternants because of the sign flipping, because of the sign of the permutation. Here they were called alternants, and this is a ratio of two determinants. So the power of this formula is that the Schur function can be expressed as a ratio of determinants. Okay, so we have given two sort of natural. So again, as I said, I will not prove this. But you know, one can use the Kostka numbers. One can prove this using careful analysis of the Kostka numbers. Okay, So, any questions about this? So, I've taken a lot of time on the Schur functions, but I guess these are important objects, so it's good to know about them. Okay, so it is natural to expand, to wonder how these are related to the other bases. So we expanded the Schur functions in the M basis, but you might want to see how they look like in the other bases. So again, they're nice sort of expansions. So here it is for partitions of 6 in the E basis, and here it's what it looks like in the H basis. So all of these are inbuilt in Sage, so you don't have to work very hard. So here this is lower triangular, that can be proven. In the P basis, they look more ugly, but these are important in representation theory. You'll get fractional numbers, and these numbers have some meaning in representation theory. Okay, so yeah, so I've shown you how this S expands in all these bases, but there is a natural expansion of the S's in the H and the E bases, which I will prove hopefully today. But before that, I just want to mention two other important identities satisfied by the Schur functions. One is called the Cauchy identity. A very useful and powerful and also beautiful result. So this says that if I take the sum over all lambda, again all partitions, I don't know what my notation for partition was, of S lambda of x. So suppose I have two families of variables. So let me say that explicitly. So suppose x equals x1, x2, etc. and y being y1, y2, etc. be two families of variables, different determinants. Then sum over all lambda, S lambda of x, S lambda of y. If I take this infinite sum running over all partitions, then I get this nice product formula. Product I j greater than or equal to 1 by 1 minus xi yj. And a similar identity is the dual, sometimes called the dual-Cauchy identity. I mean, of course, there are many things to say, and I'm just giving you a very broad overview. The dual-Cauchy identity says that with similar x's and y's. So if I again sum over all partitions, if I now take S lambda of x, but I take S lambda conjugate of y, then I again get a nice product formula, I j greater than or equal to 1 plus x. Okay. All right. Okay. So maybe with this I should move on. Oh no. Okay. Yes. So there's another thing we need to go into, which is principal specialization. So let me just define them, and then go on to other things. We need these principal specializations for data. So So it is often useful to specialize x1, x2, etc. to some specific values. For example, if you want to count the cardinality of SSYT of shape lambda with maximum entry n, then what you are doing is really evaluating the Schur function at 1, 1 up to 1, so n of them and all the rest 0, right? Because that's what we said came from the first theorem, right? So this Schur functions, when you set them equal to 1, when you set the variables equal to 1, will count standard in tableau. You cannot, of course, have infinitely many ones. But evaluating this is problematic because the formula we have for them is a ratio of determinants. But if I set if I set all the xi's to 1, I get a matrix of all ones, and which has, of course, determinant 0. So I'll get a 0 by 0 form, which is kind of useless. So what is often convenient to do is to specify. So you fix a variable. So let q be another formal variable. For f in lambda n, so let's say we only have n variables. The principal specialization of f is it's denoted ps sub n of f, ps for principal specialization. This is f evaluated at 1, q squared, etc. up to q to the n minus 1. So if you were able to evaluate S lambda at 1, q up to q to the n minus 1, and then you get a nice formula, which you get a nice thing involving maybe, I don't know, q binomial coefficients, things like that. Then there is no problem with setting q equal to 1 later. So this is an intermediate step towards counting something, and this is why we will also use them. The stable principal specialization is the limit of these as n goes to infinity. So for f in lambda, the stable principal specialization is ps of f, which is f evaluated at 1, q squared, and so on. Okay. Here, of course, you can't set q to 1. That doesn't make sense. But this could also be a nice q series, expressible nicely. So let me give you an example I leave it as an exercise. So 2. Oh, yes, I should have said that there. Okay, so then ps1 of n of f is f at 1, 1 enters. Okay, so if I put a 1 over there upstairs, that means you set everything to 1. So it's a principal specialization at all ones. Okay, so here is the exercise. So for the power sum symmetric functions, PSN, the principal specialization is has this nice formula: product I equals 1 to L of lambda, the length of lambda, 1 minus q to the n lambda I divided by 1 minus q to the lambda I. Okay, and PS1 of n p lambda. Now you just set n q to be 1. And you have to take the limit, of course. So if you take the limit, you get n lambda I divided by lambda I. What am I doing? So this A will imply B, and you will get you will get n for each term over here. So it will be n to the n. So A clearly implies B, and C is the stable principal specialization of the power sums, and this is product I equals 1 to L lambda. You just take the limit of this as n goes to infinity, and you get 1 by 1. Okay, so I mean philosophically you take the limit of this. There are other kinds of specializations, but this will suffice for us. Okay, so since I wanted, okay, so any questions about this? Okay, then let me stop recording.